All right, thanks for having me. Good afternoon. My name is Petr Zvoníček, and I work as an iOS engineer at Spotify on the mobile platform team. In our team, we focus on the architecture of UI features in the Spotify iOS and Android clients. Today, I would like to present our approach to feature architecture at Spotify. Over the years, we've developed a suite of architectural building blocks that help us align the iOS and Android app codebases more closely. The work I will be presenting today has been a collaborative effort, and I have had an opportunity to contribute to it. So let's dive right in to a brief overview of our technical environment. The Spotify music clients are available on the iOS and Android platforms, as I'm sure you already know. And these applications are developed natively, primarily using Swift for iOS and Kotlin for Android. We also have a shared C++ code base for lower-level functionalities that are common across all the Spotify clients. Our mobile code base is organized into distinct features, and each one is owned by a specific team. This structure brings us many benefits. For example, it provides a certain level of isolation between different features. It minimizes dependencies and potential conflicts between features. And it also gives teams some freedom in choosing the most suitable architecture for their feature. The iOS and Android code bases has been growing for more than 10 years. And so were our teams, in fact. Nowadays, we have more than 100 of engineers that contribute to each of those platforms daily. That has really put our architecture to the test. We have had some common shared foundational concepts, such as the design system or our backend-driven framework. But besides that, there was a little coordinated effort to align the architecture of the features. So what was the result? I think you've guessed it. The architecture started to differ between iOS and Android platforms. But discrepancies also emerged between features within the same platform, which was even worse. On iOS, we used variations of MVC and MVVM, while on Android, MVP was more typical. However, these architectural patterns are open to interpretation. And without clear guardrails, they can easily start to diverge in critical details. We realized that there was an untapped potential in being more methodical about the architecture of our apps. We aimed to implement an architecture that could be incrementally adopted, allowing us to evolve our existing code base to it. We wanted the architecture to support working in smaller contexts and minimize coupling. That's, by the way, really important for build times and keeping the build times reasonably small. We were looking for a way to build similar functionalities in the same way across both the iOS and Android platforms. And finally, it was essential for the architecture to be easy to test. So after extensive research, a few key principles crystallized to us. First of all, we realized that we did not want to do a big bang rewrite to adopt a single large-scale architectural framework. Although this approach has worked well for similarly sized products and companies in the industry, big rewrites carry a significant business risks and extensive upfront planning. Also, big rewrites often fall short of delivering on all their initial promises. So instead, we chose to build a collection of smaller, narrowly focused building blocks, essentially libraries. And those libraries can be developed and adopted separately, but we also want them to work well together. This modular approach allows us to gradually build up our architectural toolbox, enabling features to adopt new components at their own pace. Secondly, the fact that our code bases were so different presented a big barrier for collaboration and knowledge transfer between teams. This discrepancy increased the cognitive load on our teams and raised the ownership cost of our application features. So to address this, we decided to build the building blocks as a tool to better align the platforms with each other. And since I work in a platform team, we are in kind of a special position there. Our customers in my team are not really users of Spotify like you, but instead the other feature developers in the company are who we are making our work towards. And those are the people who build the features, and we kind of want them to provide we want to provide them the same products for both iOS and Android engineers. So we want to have a similar concepts and APIs available to both of those platforms wherever possible. That brings me to the declarative programming paradigm, which has proven extremely useful for aligning the concepts across the platforms. Why is this the case? Well, declarative programming has typically a higher level of abstraction. It describes what should be achieved without really detailing how to achieve it. And this helps when building platform-agnostic APIs, because we can keep the API to be as similar as possible between the platforms and align it that way. So we, of course, wanted to build upon functional programming concepts, but also, where appropriate, began incorporating domain-specific languages, also known as DSLs, that really help to build highly specialized API for specific domains. One of them, for us, have been, for example, configuring items on the screen that we also built a DSL for. An important complement to the declarative API is the runtime unit. The runtime, which essentially executes the API, can differ between the platforms and can be also adjusted to the specifics of the given platform. So the final principle I would like to discuss is our aim to create highly opinionated API. But now I hear you asking, what does it even mean for an API to be opinionated? And why is it even desirable? And here we have seen one talk that influenced us in the team where I work at strongly. It was Runar Björnsson's talk titled Constraints Liberate, Liberties Constrain, which I highly recommend to watch, even though it's from a little bit different programming environment, actually from Rust. But Björnsson there explains a somewhat unintuitive realization that by imposing constraints at one level, in our case, our APIs, we can achieve greater freedom at another level. So, for example, this constraint approach can make the API easier to understand, or can eliminate certain categories of errors and misuses. But the constraints can also create opportunities for easier automated testing of the code, and so on. So this principle has been a guiding force in our design of the building blocks. All right, so that was a bit of a theory to start with. Hope it wasn't too boring, but now I'm sure you want to see some concrete examples of how we apply these principles in practice. I will talk about 4 key building blocks based on these concepts that we developed over the course of roughly 5 years. I will provide a general overview of each block, and I'll also present the corresponding code in both Swift and Kotlin, side by side, to highlight their similarities. So feel free to focus on the language that you feel more comfortable with, just not to get too overwhelmed by the amount of it. And to begin with, I would like to discuss the state management, which I believe is one of the most challenging aspects of programming, but in particular, the mobile app development. A couple of years back, we observed a very common challenge in our code base. On Android, much of the UI and application state was spread across RxJava operator chains. On iOS, where we did not employ reactive programming, the state was scattered among view models, view controllers, and even views. This made it very difficult to reason about the state, evolve the code, and conduct testing. So to address this problem, we got inspired by the emerging unidirectional architectures like Redux or Elm. And as a result, we developed our own framework, which we named Mobius. So how does Mobius work? At its core, Mobius manages the evolution of a state value, which we refer to as the model. The model is immutable, meaning it cannot be changed directly. But instead, the changes always have to go through the so-called update function. This function defines the rules for how the model should be modified. And if you're familiar with Redux, this concept is essentially what's there known as a reducer. In the slide, the blue part represents the Mobius runtime, which knows what the latest model is and processes the updates from the update function. But now when you look at this diagram, I'm sure you must be thinking, well, something is really missing here, right? It's very incomplete and fairly useless. We can be updating our model, but like, what is it for? So the real utility of Mobius comes from how we connect this model to the rest of our application. Essentially, an environment that we perhaps have an UI or a network client in. But there are several ways how we can now interact with Mobius from this environment. So the parts of environment can dispatch an event. Event is a value type, represented as an enum or a data class in Kotlin. And when an event is dispatched, it triggers the update function to run and modify the model if needed. When the model is updated, we might want the environment to react to the change. For example, update the UI based on the model. So there's also an option for that. And there's one more data flow there, and that is that the update function can choose to dispatch external effects. For instance, one instructing a network client to initiate a request. And here it's very important to understand that Mobius does not make any specific assumptions what the external environment should be. We often bind the model to the UI, as you can see in the diagram. But Mobius is really agnostic of the environment and can work equally well as a state machine for service-level tasks, for example. So now, finally, some code. Let's look at the practical example of Mobius, of how Mobius can be applied to a simple feature. It's a very simplified one. It's a counter that can be incremented and decremented, and also can trigger very special sound effect when it reaches 0 and another decrement is attempted. So on the top, you can see the declaration of the model, the event and effect types as well. And also you can see the update function. So here we can react to the events. We can increment the model count, decrement it, and also when we decrement and it's 0, we dispatch the external effect. So this is how we want to define our business logic, basically, and the state management. And in fact, after adopting this, we realized that Mobius has had a hugely positive impact on how we manage application and UI state in the Spotify mobile apps. And one of the most unexpected benefits has been the excellent testability of the code. Initially, we recommended having one Mobius domain, that means the model, effect, and event, for a page. However, we noticed that the update function was prone to becoming quite monolithic. And although we developed several strategies to address this issue, we weren't really satisfied with any of them. And this really motivated our work on the next building blocks. And lastly, we are actually happy to have open-sourced Mobius, both the Swift and Java implementations, so you can actually find it on GitHub, complete with extensive documentation as well. So let's go to the next building block. Our next challenge here was to address a page loading. And we observed that nearly every page in our app required some data to be loaded before it could be properly displayed to the user. We decided to develop a new building block specifically designed to manage a page loading. So what is page loading about? It can effectively be modeled as a simple state machine, beginning with the loading state, from there moving to not found or loaded states, which are terminal, or error, from which we can recover by retrying the request. We started to see those small state machines in almost every page. And it's not really a complicated logic, but the complexity quickly adds up. For instance, almost every page-level Mobius update function contained such a mini state machine. So instead of having each page implement this state machine manually, we created a unified page loading building block that each page would adopt. The page block is responsible for monitoring the loading state, and it switches between the appropriate states from the loading one to the loaded one. So that's essentially all that the page loading block does. Now, a bit about how the building block is actually implemented. First, we have a loadable type. It's an abstract representation of the data source, kind of a data that are expected to be loaded, right? It's a future of the load state for a particular data, and it becomes a standardized shape of loading initial data for all the pages in the Spotify app. The loadable is then passed to the page loader class, which is responsible for starting and stopping the loading data, and also keeping the latest state of the loading. The page loader instance is then used to create a page loader view, which observes on the state changes from page loader and automatically switches between the loading, error, and loaded views. Notice that the loaded view can now expect to receive concrete loaded data, T. So no longer has to deal with any loading states at all. The page loading block has helped us to extract the common loading logic into a single library. That way, the loading can behave and also appear the same way across the pages. Currently, this page loading block supports only loading of the initial page content, so transitioning from the state of no content to some content. And that has been sufficient for majority of pages by now, but I'm sure you also think about kind of more granular data loading cases, right? If we want to load maybe like some part content on the screen. So that's something that we have actually started to research more lately, and we actively work towards kind of expanding the block too. Okay, so now we extracted the page loading logic into the building block. We realized that there's much more in regards to page standardization than just the page loading, and that we can try to do. The Spotify Music app has hundreds of pages, and they have all certain things in common. So each page needs certain input parameters to present the page. For example, content URI, if it's a playlist. It also needs certain dependencies, such as HTTP client or the playback service instance. We also need a way to navigate to the page. And inside of the page, we can define certain properties, which can, for example, be a title, supported interface orientations, but also some things that are specific to the Spotify Music app. For example, visibility of that small little player on the bottom of the screen that we call the now playing bar. But most importantly, page has some UI content that we need to have a way to create at the right moment. So to standardize this setup, we introduced page as a first-class concept in the iOS and Android apps. A high-level API for declaring the pages that promote uniformity and discoverability of page capabilities. So now to some code examples of our page building block. Firstly, you can see two type declarations. The page parameters, which for playlist is a playlist URI to show, and also dependencies, which can, for example, be the network service. Next, you can see the page declaration itself. So there are the properties of the page that I already mentioned, like the title, supported interface orientations. And there are actually dozens of more that are in our catalog and that the feature developers can choose and include there. To provide the content of the page, we use a concept called template. So template is very interesting because it provides some ready-to-use functionality that you as a feature developer can plug into the page. So it's a little bit like a catalog that you are choosing from, right? We have templates for Mobius that you've already seen. We have templates for page loading, or we have ones that support just plainly the classic UI frameworks like UIKit and Android View on Android, and also the modern ones like SwiftUI and Jetpack Compose. So template is basically a way of integrating the page with some other building blocks and frameworks that we provide. And lastly, there is the declaration of the page route, which is used to navigate to the page. In the picture, you can see the route that refers to a concrete page. In our example, it is the playlist page. And it also has a function that takes a URL and can parse it into the parameters that the page needs. So to summarize the page building block, it really gave us a high-level abstraction for declaring pages and navigation routes to them as well. It reduces the boilerplate needed to set up a page in our environment and provides deeper integration of pages into our navigation, data loading, and logging systems. Internally, it of course uses the system UI frameworks and concepts such as UI view controllers or fragments. But on the outside, we now have a declarative and standardized way of representing how the pages should be built and configured. So the last building block I would like to talk about today is Smart UI Component. It's a term that we internally use, but I'm not quite sure if it's that well used outside. So I'm going to explain it on an example. But before that, let's take a step back and look at where we currently are with our building blocks. So we have a page that is internally powered by what you have already seen. On the inside, there is the page representation building block, which is using the content template that integrates the page loading block, and also page-level Mobius domain. On top of that, we have the UI that the user interacts with. Over the time, we started to notice that for more complex pages, this pattern was no longer sufficient. The page-driven Mobius logic, as I already mentioned, was prone to getting complex. And parts of it were not easily shareable across the pages as well. So that's where the pattern of Smart UI components started to emerge. Smart UI components are essentially views which are bundled with some additional behavior or business logic, if you want. So think of a play button. We don't only want it to look the same across all the pages, which is already ensured by our design system, but we also want it to behave the same. In case of the playback button, it means taking the playback state from the same playback service, and also deliver the play or pause events to this very service. So this is an example of a Smart UI component. Now, let's look at a few more examples. These are pages full of Smart UI components. Even, actually, those are some of the most complex pages that we have in the Spotify app. And now I'm going to highlight some of them in red. You can see that some of those Smart UI components are more complex than just a play button, and they can even be nested in each other. So now you might ask, well, Smart UI component sounds a little bit like a regular view with a view model and presenter. So what do we really need here, right? What are we inventing? What we want is a standardized and highly opinionated and declarative solution for building those. We want to have some kind of a standardized interface of those components with very clear boundaries between them. And we want each to have a well-defined state as well. So that would allow us to spread the ownership of those components across the teams, right? So on one screen, you can see components that are owned by different teams with their own responsibilities for the ownership. And we can also integrate them that way more easily into various pages. And very importantly, we want the contracts of those components to be well testable. So after long research, we once again built the solution upon unidirectional data flows. That is why this diagram might resemble a little bit the one I showed you for Mobius. But while Mobius is essentially just a state machine, the key part of Smart UI component is the integration with the UI frameworks. Each Smart UI component has a single, well-defined state that you can see on top that drives the user interface. UI then becomes a function of the state, basically. State is also fully encapsulated into the component, meaning that the state is not really accessible outside of it. And the only way to change the state is through a unit that we call behavior. The behavior can change the state based on an UI event or based on some external information, for example, change of a playback state. And of course, combination of both. And we, of course, also need a way to configure the component with some data from the outside. That's what the so-called props type for. Props, it's a short for properties, which is a term that we borrowed from React. And it's an external data that configure the component. They can only be changed from the outside, and inside of the component, they are treated as immutable. And there is one more part that I won't spend much time with, and it stands a bit aside. We call it instrumentation. Each component can define a set of rules for logging of the component. And explaining it in detail goes a little bit beyond the scope of the talk, but it has been an important kind of concept for us, and it improved the utility of Smart UI component pattern for us. One of the strong parts of the Smart UI component is that it's highly extendable. For the behavior and the UI parts, we provide ready-to-use integrations, so-called adapters. They integrate other frameworks into the component and hide the complexity of such an integration through a simple API on top of it. So you can see that for behavior, we, for example, have adapters for external state publishers that we call derived state, or the one for Mobius. And on the UI side, we integrate a wide range of UI frameworks. So now let's see how the Smart UI component building block looks in code. There is really a lot going on the screen, so don't worry, I'm going to walk you through this. And let's start with the declaration of the 3 key types: props, state, and event. So in this play component, you can see that props, the external data, contains track URI, that we configure what the play component is for. In state, you can see the information, basically a simple flag, determining whether the play button is playing or paused. And in event, there are those 2 events, play and stop, that come from the UI. Next, let's discuss the behavior. This is where we define how the state should look like. And in our case, you can see that we subscribe to some external service that provides the currently playing track URI, and we map that value to the state of the component. The state mapper function, closure, gets re-executed every time the external state changes. And lastly, there is an event handler that handles events from the UI and passes them on to the playback service. Finally, the next part is the UI, where we use the state value and configure the UI with it. And we also generate events from the component and pass them on to the behavior. The last important piece is to display the play component on the screen. On the slide, you can see examples for, again, SwiftUI and Jetpack Compose. And we also have variants for traditional UI frameworks, like UIKit and Android View. So we use a special type called component view that you have to initialize with the component instance and the initial props value. So to summarize it, we have had the Smart UI components in production for almost a year now. It gave us a standardized solution for decomposing the page into autonomous and isolated components. Those components are easy to reason about, thanks to the constraints that we imposed, such as their well-defined boundaries, meaning external configuration only through props, or isolation of the internal state that is not accessible outside of it. And also explicit event type that is the way how to react to the changes in the UI. So you can imagine that this also makes the UI components very easy to test. And this standardized interface also means that the components can easily be shared and reused across the pages. So to summarize it up, I started my building blocks walkthrough with mostly page-centric building blocks. It was the modules that we used for the page state management. It was the page loading that we used for initial data loading. And it was the page representation for the page itself. But introduction of the Smart UI component gave us a way to platformize parts inside of the page itself. This was a really crucial piece that we needed to handle even the most complex pages that the Spotify app has. And before I end, there's one bonus part. I would like to share a few lessons that I and the team where I work learned while working on those building blocks. So first of all, never really start with building your own solution without researching prior art. The problem you are solving has almost certainly been solved before, and you might often end up using an existing solution. And even if you don't, which was our case that I was just talking about, you can most probably borrow some of those concepts from other solutions out there, which was certainly our case because we've been hugely inspired by solutions like Workflow from Square or Circuit from Slack. Also, try to break the barriers between the iOS and Android platforms. After all, most of the architectural problems the platforms are dealing with are fairly similar. We have had also a lot of fun collaborating on the design of the building blocks across the platforms, and I believe that it has had a positive impact on the final outcome. We spent enormous time discussing and formalizing the semantics of the key concepts in the building block, as well as naming of those. And it really pays off to know exactly what the responsibility of each is and how it should behave. For us, the most heated discussion topics included aspects of the state management or instrumentation responsibilities. No matter how hard you try, you almost certainly won't nail it on a first go. Once your library gets some users, it's important to keep revisiting the parts that does not feel quite right. But don't be afraid to make breaking changes, just make sure they are well motivated and reviewed. In Smart UI components, the part that we evolved most so far is certainly the Android lifecycle handling and the aspects of the state restoration. Also try to build real features with your library. Try to work hands-on with users of your library. It's important, especially for teams like us, where we develop the platform for others, not to lose touch with the developer experience of using your code. The building block should not be used because the company's strategy forces developer to, but because developers want to work with it. And lastly, get inspiration from the other platform owners out there. I myself borrowed a couple of ideas from Apple, for instance, such as how to engage with the internal developer community. The Swift evolution proposals were hugely inspiring as a way to document and review the evolution process of our building blocks. Similarly, the WWDC labs inspired me to internally run our own lab sessions, allowing the feature developers to book casual meetings with us, the platform owners, and bring to us any topic of their choice and bump it with us if we could help them to resolve it or improve upon our existing libraries. So that was all I had today. Thanks a lot for your attention.
Thank you very much, Peter. There's a bunch of questions, so shall we jump into it? How do you solve requirements and communication between different feature teams?
So maybe I think I a little bit answered it with my last point. We try to be very proactive and discuss, the changes and our ideas we are making in our libraries with the feature developers. One thing that's been hugely useful for us actually was to have the feature developers go to our team, spend, for example, a month or a quarter in our team to help us kind of improve upon the building blocks, basically in the way that they feel like it would be relevant for them as feature developers. So we've been trying different things, and it's definitely like a very important part not to really lose the touch with what's going on. So I think that's...
Okay, what do you think about Kotlin multi-platform? Sorry, it jumped on me, so let's, I see it. Can it be used in your building blocks to have the same architecture?
Yeah, that's a really good example. Yeah, a good idea. We've, for example, experimented with having a Mobius implemented in KMP. So far, I think we are a little bit conservative about adopting Kotlin multi-platform because after our kind of internal research, we still kind of don't feel that confident. Maybe we are wrong. Maybe it's already kind of mature enough. But yeah, it's certainly an area that we spend some time kind of investigating. Yeah.
Let's take the next one. Which music you listen to when creating this great presentation? That's a lovely question.
Oh, yeah, that's... Actually, I will confess it wasn't Spotify. It was the NTS radio. It's online radio, very music-focused. Yeah, a lot of DJ mixes from NTS radio.
Cool. Does Spotify have a dedicated performance team?
All right, yeah, we totally do. We totally do. And actually, there are two teams that focus on performance of our mobile apps. And it's something that we take quite seriously, yeah, it's been providing a very useful value. Even for me, speaking personally, we are getting a lot of very meaningful ideas from the performance team about our building blocks, and we often kind of try to incorporate them to our code base.
Okay, would you recommend this approach also for smaller apps?
I definitely wouldn't recommend to kind of build a new solution from scratch that lightly, but what I would recommend would certainly be like the more close alignment of the concepts between platforms. So if you, for example, use, there are already kind of building blocks out there that have the same concepts between the platforms. For example, the reactive extensions and different implementations of reactive extensions for different platforms. So I think that you can go quite far with just sort of treating the architecture not as a kind of separated topic between platforms, but as something that you could sort of align on.
Let's grab a couple more. How big is your platform team?
Ooh, that's a very difficult question because it's kind of difficult to say what is platform team. And like our team that made the things that I was talking about is about, let's say, 5 to 10 engineers big. So it's fairly compact. But if we talk about platform in like a greater sense, let's say mobile platform, I would say there are at least like 30 engineers, maybe 30 that work on the platform, probably more. Yeah, I'm sure this is not very accurate. Yeah.
Just say 100. Do smart UI components also handle data loading, or is data passed only using props from parents?
That's a very good question. Yeah. I think it kind of is a little bit agnostic of data loading. Certainly, passing it through props is one way where you kind of want to make the component more simple, and but there could also be a way to employ the behavior for some kind of data loading. But in general, it should stay outside. So we don't really have a kind of thought through and ready to use approaches for the data loading inside. Yeah.
Are you reusing any code across the platforms? Your architecture looks ready.
Not really code, I would say. We reuse a lot of the same concepts. The way how we work is when we make changes. For example, there is some new request from the feature developers. We try to internally in our team kind of sit down, and usually, it can be one engineer for iOS, one for Android, try to kind of make the change in parallel to both platforms, so we can sort of influence each other. So I hear ideas from the Android one, and I can also chime in with my own. So not really code, but we always try to kind of evolve the platform in the same way.
Nice. What team creates a component? Who decides on naming and so on? Having two files, iOS, Android, how do you make sure that the component changes simultaneously?
That's it's a bit tough one, in fact, because the components can be created by the feature teams. So it can be anyone who makes let's say, works on home screen, and we don't really have a kind of strong opinions on how they should be creating their components. They can create the components just for internal use. So then it's just a different file and type in their code. But there are also a special kind of smart components that are shared between different features. So we sort of have a higher standards for them because those are kind of shareable and they need to be a little bit more kind of solidly written and so on. And this is also where we want to have certain kind of a standardization in how we name them and so on.
Okay, let's take a last question. How do you enforce usage of those building blocks among all teams and developers?
I think I also touched it a little bit in my final slide. We kind of try not to enforce it by our company strategy, because I believe that it shouldn't really be enforced. Like, unless the feature developers find them useful and convenient to use, they really shouldn't be forced. So we do have a company strategy, a tech strategy that has the mention of the building blocks there. So that is sort of alignment there. But like in general, I think that should be the last resort. Yeah, primarily it should be kind of useful enough to be wanted and used.
Thank you very much. That's it. Petr Zvoníček, give him a hand.
Thank you.
Thank you, Peter.